All right, so I would say let's continue. And we will switch gears a bit now. So we talked about convergent plate boundaries and subduction zones, and I will now talk about magma dynamics. And the example I have is a mid-ocean ridge. So we will talk about divergent plate boundaries. Let me share my screen. So what I will do, a lot of the things that I will show are in the virtual machine. So the way I've set up this here is like I'm just sharing my virtual machine, and I have my slides on the left, and on the right I have this. I have the window where I show some things of how to do, like how to run models, or like how to look at them or show the input file. And so one thing about magma dynamics models is that they are like they usually take really long to run. They are really expensive. And so what I want you to do is I want you to start the model first so that it can run for a while, and then we can look at it afterwards. So yeah, if you want to follow along, the slides are in the session 4 folder on the Dropbox. But I also have the PDF over here on the left side. So what we will first do, we will go to the repository where the input file is, and then run this mid-ocean ridge model. So if you open a new terminal, you have to go to the directory that's here on the slide. What I did is I also followed along with the last tutorial. So that's the terminal window where I ran the subduction model. It just may look a little bit different for you. I just made the text bigger so that it's easier to read. But basically, you can see down here, I'm already in the ASPEC tutorials folder in the session 3 folder. So if you already ran the last tutorial, the only thing you have to do is you have to go up one directory and then go to the session 4 folder. And so I think we've mentioned this a few times, but if you want to be faster following along typing, if you're not familiar with using Linux, what you can do is you can start typing something and then hit tab, and it will auto complete a word for you, or like it will also complete folders for you that are already there, or files that are already there. So that's why if you see us typing something in the terminal, that's why we can do that so fast. Okay, so we go to this session 4 folder. So if you ran the last tutorial, you can just simply use this command. And otherwise, you have to do what's over here on the slide. And then we want to start the model. I have the command over here. So I would recommend really using as many processors as you have on your virtual machine, because it will take a long time. And so the more processors you have, the faster it will be. So what I've done over here is I just put an X, where X is the number of cores that you have on your virtual machine. So I will also do that here. And well, the other thing I want to mention is the ASPEC executable that I use here is the one that we compiled in release mode. And so that if you didn't compile the release mode, if that didn't work for you for some reason, you can of course also use the debug mode, but the release mode is much faster than the debug mode. So if you have the release mode, I would really say use the release mode executable here. And so yeah, so what I'm doing here is I use the link that we created in the ASPEC repository. If your release executable is somewhere else, then you would have to use the links to your release executable. And then the last thing is the name of the input file, which is called midoceanridge.prm. So, I will not do that right now, but just to show you in that folder where we are right now, if I type ls and see what's in the folder where we are right now, there's this mid-ocean ridge PRM. There's another PRM for restarting. There are there's a folder with like restart files, and this one is just the same model that I already ran, just in case it would take too long so that I could show the results anyway. All right, so let's all start this model. And well, so if your subduction model is still running because it was slow for some reason, what you would have to do is you first can hit, you can always hit Control-C to cancel a model run. So if your other model is still running, I would say don't run anything else at the same time, hit Control-C to stop the subduction model, and then start this one. Okay, so I hope you could all follow along. So let me start this, and I will immediately aborted because there's something else that I wanted to show you, but you can continue letting this run. And what I wanted to show is that I wanted to talk a bit about how to reference ASPEC, how to cite ASPEC if you write a paper with ASPEC. And so the idea about this is basically, well, if you sort of one key part about if you like do research with code or like any type of research in general, you want your research results to be reproducible. And so basically there are two keywords, reproducibility and replicability, with like slight differences between them. But basically one thing that's important is what you want to do is that someone else can take your input files and the ASPEC version that you ran and then just like use those tools and recreate the same result that you got. And the more different software tools you use, the more complicated it becomes to be able to do that. So in general, what you would probably do is you can share your input files as like some supplementary files or as a link to a repository if you like with every paper you publish. But then you also need to tell people, like, it's not enough to just say, oh, I used ASPEC, because there are different versions of ASPEC. You also, so we talked a bit about this on one of the last days, you also want to say, well, this is the exact version of ASPEC I used. And if you made any changes, you also want to say, well, these are the changes I made. And if you didn't make any changes and just used an ASPEC version, we already said, well, ASPEC automatically tells you what version it used for running this model. So this one says it's version 2.2. And it also tells you what are all of the versions of the libraries that that ASPEC used. So ASPEC relies on these different libraries like DEAL2 and Trilinos and pforest. And so ASPEC also reports these different versions here. And that's the one thing. Basically, if you publish a paper, you always want to say, well, I used this version of ASPEC, or if you didn't use a specific release version, as you see over here in the slides, it will give you a commit hash. That's basically like what specific commit, what like if it's not a release version, people make changes and all of these changes are made as commits. And so this is basically a unique identifier that tells you what version of ASPEC did you use. But in addition to that, in addition to making everything reproducible, we also want to give credit to everyone who has worked on the development of any code in general. So this doesn't just go for ASPEC. It's like there are people who put a lot of work into developing these codes. And so it's only fair that they will get credit if someone uses these tools. And so in ASPEC, what we try to do is we try to make that easy for you. So every time you run a model, at the start, it will create, so at the start of the model run, you will see that it will give you this link. And you can, and this will also be output at the end of the model run. So if I scroll up to the selection model, there's also a link that's at the end of the model run. So that's like the last thing that happens. And so what you can do is you can click on that link. So let's just say open link, and then you get to a website where we've already put together some information of how you can cite ASPEC. And basically what we've put here is how would you write that in sort of the main text of a publication? How would you write that in the acknowledgements? And also what references would be like what reference we ask you to include if you have used ASPEC for any research publication. And so there's a list of a number of things. One of these, so some of these are the sort of the methods papers that we published with ASPEC. One of this is the ASPEC manual, and one of this is also a direct citation to the software. So this one here, so one of these is just basically just the software aspect. And what you notice here is there's also this other, like this last paper, that's one that I wrote together with Timo, and that's just about the macromantle dynamics. And so this doesn't always show up if you click on that link. That depends on what model you've run. And also if I scroll up here, you see that there is this green box where you can check a number of different boxes, and the box that's already checked is melt transport. And the reason for this is that the model that we're running here is a model that includes this magma dynamics functionality. And so because sort of Timo and I were the people who started implementing this, Because of that, we also ask you to cite that paper that describes how we did the implementation. And if you use other features and click on this link, these other boxes will be pre-checked. So for example, if you use a free surface, or if you use particles, or whatever, so let me just click on this free surface, then another paper will show up here. That's this one. That's about the implementation of the free surface. And so I just, so basically what you would have to do is just copy, well, if you use BibTeX for your publications, copy all this here below, or otherwise copy this part and just add that to your publication and then say, I use ASPEC, this and this version, and then cite these different references. And that's just what we ask you to do if you use ASPEC in your publication. And we would be very happy if you could give us that credit, because we also need to show that we've done something useful. We developed ASPEC and people use it, and it's useful for the research community. All right, so that was everything I wanted to say about this. So let me also run the model, so that will run in the background. And so while that runs, what I want to do is I want to go through the input file just to basically show like what is this model setup that we are running here now. Yeah, and sort of how did we set up a mid-ocean ridge model? And so that's the first thing I want to talk about, the input file. Then I want to look a bit at the model output. And then afterwards, I want to talk a bit about like how magma dynamics works in general, because it's something that's like, it's not as common as modeling like normal mantle convection or like lithospheric dynamics models. So it's something that not as many people do. And then if we have time, I will talk a bit about the methods of how that's done in ASPEC internally. And in the end, I will have some suggestions for how you could play around with that model. All right, so for the model setup, so there are different ingredients that should be included in a model. And I've just listed some things here, like what are the equations that we want to solve, what's the model geometry, what's the mesh of the model, what are the material properties. And we've basically looked at like all of these things. We've looked at this for all of the other models we've been running in the past few days. And we will do that again for this mid-ocean ridge model. So the input file is in that folder where we just went to start the model. So it's in the ASPEC tutorials, 2020 Tectonics modeling tutorial, and then session 4 midoceanridge.prm. And so let me open this. I usually just go to the file manager. So I click on this button up here that has the file folder, and then I can go to the ASPEC tutorials folder, the modeling tutorials folder, and then I go to session 4, which is the magma dynamics part. And then here there's this midoceanridge.prm file, and then I just use LeafPad to open it. And so then we see this file. And one other thing I want to say about this is basically, there's also a cookbook in the ASPEC, like so in like with all of the other ASPEC cookbooks, that's also called Mid-Ocean Ridge. And this is basically the same setup. And the only changes I've made is I've reordered it a bit so that it's easier to follow along with the slides when I go through the input file. And I've made a few changes that make it run faster, because as I mentioned, these magma dynamics models they always take a long time to run because it's just such a complicated problem. And so I just wanted to make it run a little bit faster. But otherwise, this is the same as the Mid-Ocean Ridge cookbook and the ASPEC manual. All right, so let's go through this input file and see what the model setup is. So in general, what we're doing is we model a mid-ocean ridge where we model half of a mid-ocean ridge. So the left boundary of the model will be the ridge axis, and then the top boundary of the model is sort of, that's where the plate moves away from the mid-ocean ridge towards the right. And so what we expect is there will some melting will happen at the ridge axis. And so we will have a region where there's like both melt and solid present, and where we want to solve the coupled equations of magma mantle dynamics. And then for the rest of the model, where there's no melt, we want to solve the normal Stokes equations that we've been solving in all of the other models. And then the temperature is of course also important if we want to have like melting and the freezing of melt. And so everywhere in the model, we also have to solve the temperature equation. So we want to have at least like heat advection and diffusion of heat in that model. And so for the melting and freezing, the other heating process that we want to have is we also want to include the latent heat of melting and freezing, because that changes the temperature a lot and it influences how much melting will happen. So if we go in the input file, so the first things I won't talk about that much today. So we run the model in 2 dimensions. The output directory is called mid-ocean ridge, and we set the end time to 8 million years. But then the first section here is about the equations. And so for all models that run that want to include these magma dynamics equations, there's a separate section that's called melt settings. And in this section, we have to say we want to include melt transport in the model. So that's this parameter. And only if that's set to true, then we have this region here where we solve the magma mantle dynamics equations. And this, and the other thing we wanted to, that also changes the equations is this heat advection by melt. So basically what we want is if there's melt present and if that moves around, that should also transport heat. And the only reason why that's something that you would ever switch off is because it just complicates the model more. But like physically, that's always the correct thing to do. And the other thing that changes the equations is down here. In the heating model, there's the subsection heating model where we can switch off or on all of the heating terms that we want to include in the temperature equation. And so in our case, we say, well, that's only latent heat and no other heating processes. And so just one thing I wanted to show, or I wanted to repeat again, what I have here on my slides to the left is how that would look like in ASPEC's parameter viewer. So if you go to the ASPEC website, so if you go to aspec.geodynamics.org, so I think we've mentioned that before, but basically if you go to that website, there is a button here that says parameters. And if you click on that button, you get to this parameter viewer that lists all of the input parameters. And so I said, well, we looked at what's important is the melt settings, and the other important thing is the heating model. And so if you click on this, you see, so in the input file, I've shown that, well, the model that we're using is just latent heat in this list of model names. And here you can see what all of the other options would be. So all of the heating models that we don't include are, for example, like adiabatic heating or radiogenic heat production. So there's like this radioactive decay or shear heating. And if you click on this, it will also show a documentation of all of the other heating models. And so basically what we're saying is we only include latent heat. And so if you ever have any other questions about the parameters, you can also look them up here in this parameter viewer. So that's just what I will show on my slides. All right, so we said for the equations, we want to have melt transport and we want to have a latent heat in the temperature equation. Then the next thing we look at is the model geometry. So this is a Cartesian geometry, and we want to have about like a bit more than 100 kilometers in horizontal direction and 70 kilometers in vertical direction. And well, the reason for that is basically just we want to the depth of the model should be below where the melting starts, and we want to extend it in vertical direction so that we at least like include most of the melting zone here in our model. And so that's the geometry, and then we also so there's also the gravity that points downward in that model. And so the section in the input file that covers this is over here. Model geometry. So that's similar to many of the other models we looked at. In the geometry model, we say our model should be a box. The x extent should be 105 kilometers. The y extent should be 70 kilometers. And again, we also have these repetitions for the mesh to say we want to have approximately an aspect ratio of 1 for all of our cells. And for the gravity, we say, well, it should be vertically pointing downward, and the magnitude is 10. And so the next part I want to talk about is the material properties and the melting and freezing that happens in the model. And so I don't want to talk about all of the details of the material model. So if you look at the input files, there are only a few things listed here. If I go to the parameter viewer here, so if you go to the parameter viewer and look at this melt simple material model that we use, you will see that there are a lot of other parameters that I just haven't listed here. So that means the default values will be used for those parameters. And one reason for that is that so if you go there are all of these parameters A1, A2, A3, and so on, and they relate to the melting model. So this so the melting model we use is a published melting model that I've also shown here as a small image from Katz et al. 2003, and so that has a lot of parameters, and they are also all included as the parameters in that material model. And so
Juliane?
Yes.
Can I ask a quick question? We had a question in chat if the heating models are additive, which they are. So whenever you add a new plugin, it will be added to the heating of the others, but also if they are non-overlapping. So if they are exclusive. So for example, should I add adiabatic heating and adiabatic heating of melt, or should I always just add one of them?
So, well, I guess I would say that's specific for each of the models. So I would say always look at the documentation. For the case of adiabatic heating and adiabatic heating of melt, you have to add both of them. So basically I guess that's what I think what you have to do. I would read the documentation, but I think that's how it is. So I think what happens is if you have a model without any melt, you would have to add adiabatic heating, and it adds the adiabatic heating term. And what happens in the case that you also have melt is, so the adiabatic heating term is something like the thermal expansivity times basically the solid fraction, and then something with the velocity of the material. And so what happens is if you have melt, that your solid fraction is no longer 1 anymore, so you basically have to subtract something. So you basically have to multiply this term of the solid by the solid fraction, and then add the adiabatic heating for the melt with the melt fraction, which may have a different density. So these terms may look different. So I think what happens is that, well, let's look at the documentation. So the way you would go about this is you would say, okay, we have this list of model names, and there's adiabatic heating and adiabatic heating of melt, and I want to know what they do. So adiabatic heating of melt. And so it says what term it implements. It implements the term thermal expansivity times temperature times sort of minus the melt fraction, so the volume fraction of melt, times the solid velocity times the pressure gradient, and then thermal expansivity times the temperature times the porosity times the melt velocity. For full adiabatic heating, this has to be used in combination with the heating model adiabatic heating. So in this case, you have to use both. But in general, I would say if we wrote the documentation properly, it should tell you if you have to use them together or if you have to use them separately. So for example, I would say for example, for radiogenic heat production, there are different types of models, and you probably don't want to use more than one. So there's like this radioactive decay, and there's constant heating, and they will all just add different terms, and you just have to decide based on what model you run if you want to add all of those or if you only want to add one of them.
Okay, thank you. A different question was about if melt models are extended Boussinesq approximation or compressible. I'm not sure if you will go into that later.
I won't go into that later, so let me answer it right now. The the simple answer is you can pick. Let me go to the melt. Oh, let me go to the material model. So in the material model, there is this melt simple model, which is the one that we're using. And so that has like a solid density and a melt density, but it also has a solid compressibility and a melt compressibility. And so by default, they are set to 0. And there's also a parameter that's called useful compressibility, and that's by default also set to false. So in our model right here, it's, well, I would even say it's Boussinesque, because we don't have adiabatic heating and shear heating, so it's not even extended Boussinesque. So it's basically just Boussinesque. We assume constant densities, with the only difference that the solid density and the melt density are different. So I don't know if you would still call that Boussinesque. It's basically Boussinesque individually for the solid and the melt. But if you and the reason the reason that's probably fine for this model is that it's only 70 kilometers depth, so the density will probably not change that much with depth. But if you want to include full compressibility, you can do that. You just would have to switch this parameter to true, so use the full compressibility, and then put in your compressibility for the solid and for the melt, and then it will be a fully compressible model.
And in this case, we don't have to change anything in any other subsection, because the melt solver always handles things as compressible. So just for reference, if I would want to change the normal ASPEC model from an incompressible model to a compressible model, I would have to change something in the subsection that's called approximation, or yeah. And for the melt, that's likely not the case.
Yeah, I don't think you have to change anything else anywhere. I think so.
Okay.
Yeah. And there is also, so if you want to run the compressible model with melt, I think there is one that well, I don't even remember if that's a cookbook. So, but at least in that first paper, we have, well, in that paper that I mentioned, I have it, I have a link to it on my last slide. There are some models that are fully compressible, and we included the input files with that paper. So yeah, that would be some examples to look at how to run a fully compressible model.
Okay, so the general advice would be find a model that is as close to what you want to do and start from there.
Exactly.
Okay, thank you.
All right. Yeah, so let's go back to the material model and to the parameters that we are changing here. So, well, as I mentioned, if we look at this in the parameter viewer, they are all of these different parameters that I have not included here because they will just stay at their default values. And so the only thing I've changed here is the permeability. I've made it a little bit smaller to make the model run faster, and I will talk about what exactly the permeability is later on. We will play around with this a bit. And the other thing that's that we should maybe talk about a bit is this melting timescale for operator splitting. And so basically the idea is here that in this model we have the melt transport, but we also have the melting and the freezing of melt. And that may happen on a different timescale. Usually it's much faster than the melt transport. So usually, well, for most scenarios, we assume at least for melt transport in the sublithospheric mantle, the melt is in equilibrium with the solid. So basically the reactions happen much, much faster than the transport of melt. And so because of that, we use a solver scheme, this operator splitting solver scheme, that lets us use a different time step for solving the equations of melting and freezing and solving the transport equations for the melt and the solid and everything else. And so because of that, we have to set sort of a time scale for the reactions here. So we have to set a freezing rate, and we have to say sort of what time step these reactions should use here. Well, let me go back to the slide I wanted to show. And so this one also has a parameter. So we define a reaction time step, which in this case is 400 years. But what we also want to say is at the same time, we want to have at least 10 of these reaction time steps per transport, like per advection time step. And so whatever causes the smaller reaction time step will happen. So the time step will be never bigger than 400 years. But if the advection time step is smaller than 4,000 years, then it will become even smaller in order to have at least 10 of these reaction steps per normal time step in the ASPEC model. Yeah, and some of the, like this parameter here is just to make the solving faster and more robust. All right, and I will talk about the material properties a little bit later on. So basically there are like we have the same material properties that we would have for a normal mantle convection model, like what is the density and what is the shear viscosity. Just in our case, the viscosity will be influenced by how much melt is present in the model. And we also have new material properties that are important for the transport of melt. So that's, for example, this permeability here that also depends on the porosity. And that's this something that's called the bulk viscosity. And I will talk about so we will change the material properties later on and see how they change the model evolution and what they do. But then the other thing we need for our model setup are initial conditions and boundary conditions. And so for the initial conditions, what we want to do is we want to say, well, it's it's a plate. We start with a cold boundary layer that has like a fixed cold temperature at the top, and then has some sort of like a half space cooling model. And at the bottom, we want to have a temperature that corresponds to something like the mantle adiabat. So below that part where the plate is, we want, so we use so we don't use adiabatic heating, so we don't have an adiabatic temperature increase. So below that, the temperature should be constant. And one way to do that as an initial condition, so if we talk about the temperature now, is shown in that section here. In the section initial temperature model, the model name is called adiabatic. That's a little bit confusing because, well, we said we don't include adiabatic heating, but if adiabatic heating is not included in the model, or if the thermal expansivity is 0, then basically what happens is it's just sort of whenever we would have an adiabatic profile, that's a constant temperature. But the reason we're using this here is that it also includes this half space cooling model. So we can include a cold plate at the top of the model. So we set the H of this top boundary layer. And we also have a thin boundary layer at the bottom. And so that doesn't really explain how that would look like in the model. So I would say even like our model may still be running, but we can already have a look at how that initial condition looks like. So we can open the model in ParaView and look at, well, what is this initial condition that we picked here? And so to open ParaView, I usually click on this mouse symbol here. And then in the window, you can start typing in ParaView. And then it will just show you here the ParaView client. And then you can click on that and it will start ParaView. And then we can open that model by clicking on this folder symbol here to the left. We've done that several times before. And then navigate to where the output of our model is located. So in this case, it's in ASPEC tutorials, then the Tectonics modeling tutorial folder, then in session 4, which is where we also ran the model. And then there should be this. So you probably only have 2 output folders, and one of this should be this mid-ocean ridge one. And then what we want to open is the solution.pvd. And sort of once we've loaded that in, we have to click on apply, so that we see that here in the window, and we can, like, again, this warning message will show up, and so we can just close that so that we don't see that anymore. And now that we have that loaded in here, we can change the representation from solid color to temperature. So instead of just having this gray box, what we want to see is like, what is the initial temperature in the model. And so if we click on that, we also get the color scale here. And so we basically see how our initial temperature looks like. So as I mentioned this, we have a really thin hot boundary layer at the bottom with about 1600 Kelvin, which is our sort of the mantle adiabat that we assume. And at the top, we have a big boundary layer that corresponds to sort of a really old plate. And the reason I chose that age so big is that basically means there is no melt in the beginning of the model, and the melt will just will be generated over time in the model. And we can later on look at how this happens. So yeah, so that's the initial temperature.
Juliane, can I ask another question?
Sure.
So this is probably a bit more advanced question than that you wanted to cover in this tutorial. But we had the question that if you assume equilibrium thermodynamics, you can calculate melting and freezing rates using, for example, the enthalpy method, like in the paper by Katz et al. So if you have an enthalpy table, you could compute the equilibrium melt fractions. But it looks like in this model, we don't seem to do that. Does that mean how does our melting model work here? How do we move towards an equilibrium melt fraction? I already explained that we use a simplified approach here.
Yeah, so like I wanted to explain that later on. I have that in my slides. I hope we will get to
maybe
that.
we
So
just we can also postpone that for later.
Yeah, so maybe it's better to, so I hope we will get to that. I didn't expect so many questions, but basically I have some slides here where I talk about the melting model. And so the only thing I want to say right now is this melting model is really simplified, the melting model that we use for this model. And the only reason for that was that sort of the CAT 2003 is a really popular model that like lots of people use in general in like mantle convection models. And so that was just the first one that I included in ASPEC, but it doesn't predict a composition of the melt and of the solid. And so because of that, it's not thermodynamically consistent. And like later on, I will go a bit more into detail about like what we do in this model and how you would probably want to do it differently if you implemented your own melting model.
Okay, yes. Thank you.
All right, so we were, yes, initial conditions. So we talked about the temperature initial conditions, which is basically like having a cold top boundary layer and then having the potential temperature at the bottom. And sort of having a half space cooling model between those two. And then we also want, we also have a composition in our model, and we also need initial conditions for those compositions. And just to say a bit about the compositions in general, so that's in this composition subsection here in the input file. We talked about that a little bit, and like for some of the other models, this material model also expects specific compositions to be there. So you always have to have a compositional field that's called porosity, and you always have to have a compositional field called peridotite. And if you don't have that, ASPEC will just crash and will tell you you need those compositions if you want to use the melt simple material model, because it assumes that those compositions are there. And the reason for that is basically that if you use a model that includes melt transport, you have to have a field that's called porosity, and then that will be used as the field that tracks the volume fraction of melt. That's present at any time in the model. And just sort of giving it that makes sure that it doesn't matter in which order you put in the compositional fields here, it will always use the field that's called porosity, and will also always be called porosity in the output. The other field is something that's a little bit more specific to that material model. And the reason is that, as I mentioned, the CAT 2003 melting model, that doesn't predict like a specific melt and solid composition. But one thing that we can do in order to predict the equilibrium melt fraction is we can track something like a depletion. And that's what the field peridotite, what that does in the model. So if we, later we will also look at it, but it basically tells us how much melting has already taken place in the model in that spot where I am here. So if you melt 10%, and then it doesn't matter if you take the melt out or leave it there, this peridotite field will remember that you've molten 10% of the material in that place. And also if you freeze melt somewhere else, it will also track that sort of like, so it will be a tracker for something like depletion and enrichment. And so for like, if you want to use that material model, those two fields have to be present. And then the initial conditions that we want to start with is we want to say, well, there shouldn't be any melt anywhere in the model. And we also want to start with no depletion or enrichment in the model. We want to start with like an average periodic mantle composition. And the way to do that is setting both of these fields to 0. So we will use the initial composition model that's called function. We've already seen a lot of these function models in the last few days, where we set variable names and we set a function expression. And in this case, it's really simple. It's just like both of the function expressions are 0. And so if like for compositional fields, you have to provide one function for each composition. So basically that's the first one for the porosity, and then there's a semicolon, and that's the second one for the peridotite field. So we said, okay, we have initial conditions for both the temperature and the composition. And now we also need boundary conditions. And so we need boundary conditions for the velocity, and then also for the temperature and for the composition. And so if we can sort of go back to the, so let's first talk about what kind of sort of velocity boundary conditions we want to have. So we said, well, the left part of our model, that's the ridge axis. So we know we want the model to be symmetric about the ridge axis, so we make this a free slip boundary where material cannot move through, but it can freely move along the boundary. Then we also know we want to have a mid-ocean ridge here, so we want to prescribe a velocity at the top so that material moves towards the right. So we prescribe the plate velocity on top. And then we don't really know what sort of velocities we should have at the sides and at the bottom. We basically just want to say, well, whatever flow that plate velocity here at the top causes, well, that's how we want the material velocity to be. So there should probably be some inflow at the bottom and some outflow at the side. And so what we do here is we prescribe the lithostatic pressure as a traction boundary condition at like both the right side and the bottom of the model. So basically what we do is we prescribe the stress at those boundaries instead of prescribing the velocity, and then the material can flow in and can flow out. And because we know how the flow field will look like, basically material will flow in at the bottom and flow out at the right side of the model, we know we have to prescribe both the temperature and the composition at the bottom of the model because the material flows in, so we have to give the inflowing material some properties. And we want to set the temperature to the potential temperature of the model. And well, we want a 0 melt fraction and a 0 depletion of the material that comes in. And then in addition to that, we also have to prescribe the temperature at the top so that we maintain this cold boundary layer here at the top. So we set it to like 20 degrees Celsius. So basically, common temperature at the surface. So the way to do that in the input file is, for the boundary temperature model, that's very similar to some of the other models we looked at. We said we fix the temperature at the top and at the bottom boundary, and then we use the box model that allows us to set these temperatures. So at the top we use the 293 Kelvin, at the bottom our potential temperature. And then for the composition, if we go down here, that's something that I really like to use. So for the boundary composition model, we fix the boundary composition at the bottom of the model. And then the model name is initial composition. That's something that I find really convenient to use for the composition because it just takes whatever we defined in the initial composition model and then uses that at the boundary. And then the new thing that we haven't talked much about is sort of the velocity and the traction boundary conditions. So that's in this velocity subsection here. Because we have both these velocity boundary conditions and the conditions for the stress, we have to have two subsections. So we have a boundary velocity model and we have a boundary traction model that's down here. And so for the velocities, we said, okay, at the top, we want to prescribe a function. At the left, we want to have free slip, so a tangential velocity boundary indicator. And for the function, I said we want to prescribe the plate velocity. So in this case, I just picked a half spreading rate of 3 centimeters per year. So 0.03 meters, that's what this variable u0 here does. But then if we think about that, if we just prescribe a constant velocity at the top, that may cause numerical problems right in the corner here, because free slip says nothing can sort of penetrate the boundary, but the prescribed velocity says, oh, we want to have like a horizontal velocity. So that corner then like that, like it will have sort of different boundary conditions from the boundary of the left and the boundary at the top, and it will just pick one of these, but it will probably cause like really big gradients in the velocity in that corner, and we don't want that. So what we do to fix that here is, instead of just prescribing this u0 as the x component of the velocity, we say, well, if we are closer than 10 kilometers to the ridge, we interpolate between a 0 horizontal velocity and between this velocity of 3 centimeters per year. And so that's what this first part does. It just uses a quadratic function and says, well, directly at the ridge, the horizontal velocity is 0. And if we go 10 kilometers away from the ridge, which is this x0 value, then we have the velocity u0, which is 3 centimeters per year. So that's the velocity boundary, so the one we prescribe at the top. And then the traction boundary, we said we wanted to prescribe the lithostatic pressure. So we say we want to have 2 boundaries where we have prescribed traction boundary indicators. One is the right boundary, the other is the bottom boundary, and you don't see that part because it's further to the right, but both of them we prescribe the initial lithostatic pressure. And then this initial lithostatic pressure model that has one parameter that you always have to set. That's basically at which point should it compute that initial lithostatic pressure profile. And so in our model, it doesn't really matter because the initial condition is basically just 1D. It doesn't change throughout, like it doesn't change with the in x direction. But what I just said is like the representative point where I want to compute that 1D lithostatic pressure profile. That should be at the right, sort of the right boundary at the model. And then what ASPEC does is it starts at the top with the surface pressure and then sort of integrates downward to compute what's the lithostatic pressure. All right, so those are the boundary conditions. And then the next thing, I maybe don't have to talk about it that much because we already talked a lot about mesh refinement for all of the other models. So what we said is, well, we have this model, it's like 70 kilometers times 105 kilometers, and we had these repetitions, so 3 repetitions in x direction and 2 repetitions in vertical direction. And so the coarsest mesh would look something like this. And then we want to have 4 initial global refinements, and we said for each of these refinements, we double the resolution. So if we have 1 global refinement, the mesh would look like this. So we cut each cell in half in each direction. And then for 2 global refinements, it would look like this. And we just do like 2 more. So in total, 4 of these global refinements. And then we also have 1 adaptive refinement. And what we say is we want to refine the mesh in parts of the model where melt is present. So we also have this minimum refinement function that we talked about before as a mesh refinement strategy. So that basically says, well, we want to have a minimum number of refinements everywhere in the model domain, but it depends on where we are in the model. So this subsection says what exactly happens. It says, well, if our vertical coordinate is above 40 kilometers, so if we are in the uppermost 30 kilometers of the model, then we want to have a minimum refinement of 4. And if we are below that, so if we are in the bottom 40 kilometers of the model, we only have a minimum refinement of 3. And so then in addition to that minimum refinement function, we want to refine where melt is present. And so that's what this other refinement criterion does. It's called composition threshold. And what that does is for each compositional field, you can set a threshold. And if the field is above that threshold, the mesh will be refined to whatever the maximum number of refinements is that are allowed in that model. So in our case, we have like 4 global refinements and 1 adaptive refinement. So the highest refinement level that can happen in the model is 5. And so the down here is that subsection for the composition threshold. And so for the second field, it's 1. So we will never reach that. We don't care about the second field. What we care about is about the first field that was called porosity. And threshold here is 0.25. So wherever there is more than 2.5% of melt, we want to refine the mesh. And so then what would happen, just to illustrate it here, in regions where melt is present, it would adaptively refine the mesh. And I also wanted to talk a bit about like what resolution do you need in these models with melt, because we've also had a few questions about like how do I pick a resolution? How do I know what the right resolution is? And so I made a slide about this because we actually tested what resolution you need. And so one thing I want to say is the resolution that we have here is coarser than what you would need just to make the model run fast. And we just if I zoom in here for a bit, what we see here on the slide on the right, this is a different model of a mid-ocean ridge, where basically what you see is just the part, like the left boundary is again the ridge axis, but what you see is just the part that's really close to the ridge. And we ran it in different resolutions. And I just put here, put a scale on here. So the smallest square, the one that's solid, that's the 1 kilometer resolution. And so this model has 1 kilometer resolution. This one has 500 meters for the cell size, and this one has like 270 meters for the cell size. And what you see is that basically if the cell size is 1 kilometer, like down here, you have this channel, and with a cell size of 1 kilometer, you don't really see that channel at all anymore. And for it to be like sort of well resolved, you need this resolution of 270 meters. And we also ran like coarser models and finer models and looked at, well, can we sort of quantify some properties in the model and look at like which resolution is needed to sort of get a deviation of a given percentage from what sort of the best result of the highest resolution. And so that's what's shown over here to the left. So
Juliane, can I ask a quick question? What do you mean by a channel? What is the feature in this picture that is the channel, and what is important about it?
Well, so I will come to this, but basically to I haven't labeled this. What's the color shown in the image is the porosity. So that's the amount of melt that is there. And so there is a channel of melt that's basically, so everywhere where there are these orange colors, there's melt, and everywhere where there are these brown colors, there is no melt, and a channel of melt forms, which is basically the base of the lithosphere. But so it's not really important what this feature is. It like what's important is that there is some sort of like feature in the model that's not shown in this model, but that's shown in this model, and we want to know what resolution do we need to show it, depending on how wide the feature is. So it's a channel of high porosity, and so if you look at the scale, it's a bit more than 1 kilometer wide. And so that's what I wanted to show here in that plot. The x-axis shows basically a length scale, where I've marked as this gray line is like the width of the feature that we want to resolve. So in this case, it's this melt channel that's a bit more than 1 kilometer big. And the dots here are the different, like is the resolution of the different models that we ran. And what's shown on the vertical axis is the integrated melt flux in 3 kilometers depth. So what we did was we looked at we went to 3 kilometers depth in that model, and we looked what's the melt flux vertically across that depth. So that's like the melt fraction times the velocity of the melt. And we sort of ran lots of models with different resolutions, and like based on that extrapolated what's the melt flux you would get if you had an infinite resolution. And then we basically said how different would it look like with these coarser resolutions. And so that's what this vertical axis is. So you see it like with higher resolution, it converges to some value over here. And what we find is basically if you want to have a melt flux that's accurate of up to 1%, so that would basically be this model here that's that's closer to 1% of deviation from the sort of infinite resolution model, then you need a resolution of like something like 250 meters. So this one is 250, this one is 150. So you need a resolution of 150 meters to have 1% of error for a feature that's a bit more than a kilometer wide. So you need something. So in general, as a rule of thumb, from this model and also from what other people have said, you often need something like 15 mesh cells per length scale of the feature that is resolved. So in this case, that's a little bit less, but so that's just, so of course you always have to do like resolution tests yourself if you run a model, but I just thought I wanted to show this because it's more than what you would expect. It's like basically even this model down here where you think, oh, everything looks well, you may want to have a higher resolution than this. And so if you want to have more details, you can have a look at this paper. I will also have a link at the on the last slide, but I just wanted to give that as a sort of idea for like what resolution do you need to pick in these models with melt. All right. Yeah, and so you could choose different criteria for refining the mesh. So yeah, I haven't talked. Yeah, I will talk about this compaction length later. I've also marked that here on the slide above. So the compaction length is basically a length scale, like a typical length scale for features in models of magma dynamics. And so that length scale is much bigger than, for example, the width of that channel of melt that develops here in the model. And so what I wanted to illustrate by this is just that if you just resolve the compaction length, that's not enough. You have to have a much finer resolution. And also we tried using this compaction length as a refinement criterion. So that's what you see in this image here. So the image to the left shows how the mesh would look like if you just refine everywhere where melt is present. The image to the right shows if you refine based on the compaction length. And we tested different criteria, and basically what we found is what you really want to do. Well, it first depends on the type of model you run, but one strategy that's useful is define based on the either the melt velocity or the fraction of melt, so based on the porosity. So something like everywhere where melt is present. All right, so let me go to the last part, for the last part of the input file, and then maybe we can make a break and look at the model afterwards. So the last thing I wanted to talk about a little bit here is the solvers. So someone had a question that was like, well, in which case do we have to use a nonlinear solver, and in which case can we say, oh, we just do like single advection, single Stokes? And in the case of so in general, that depends on like if you have a linear problem or if you have a nonlinear problem, and where the nonlinearity is. And so in our case, it's a nonlinear problem, not just for the Stokes system itself. So basically in these lithosphere dynamics models, the biggest nonlinearity was that the viscosity, which is part of the Stokes equation, depends really strongly on the amount of deformation. So the strain rate, which is also part of the Stokes equation. And so that's because of that, you have to iterate over the Stokes system, because that's like a really strong nonlinearity, and there's not such a strong dependence between the Stokes and the advection system. So for example, many of these models didn't even have a temperature dependent viscosity. But that's different for these magma dynamics models, where we have a number of different material properties that all depend on the amount of melt that's present, so on the porosity, which is part of the advection system. So it's solved as a compositional equation. And so we have to iterate between the Stokes and the advection system. So that's all the way at the top of the input file. So our nonlinear solver scheme is iterated advection and Stokes. So that means for every time step, we solve the advection equation and the Stokes system, and then we check if we are below our like if our residual is below a given threshold, and if not, then we solve both equations again, and then we check again until we reach convergence. And what I already mentioned is this operator splitting, that we have then a different time step for the reactions. Okay, so I would say the next thing we want to do is like looking at the model output, but let's take a break for 10 minutes and then do that afterwards. So we will come back 10 minutes after the hour. Or Renee, did you want to say?
Yes, that sounds good. So let's meet 10 minutes after the hour. We had one question in the chat that may be worth mentioning for everyone, and that is why is temperature not considered a compositional field like all of the other properties that we put into compositional fields? And so what's the difference essentially? Why is temperature something special compared to all other fields? And I already put into the chat that this is, well, it's partly a decision, partly it's an historical accident. We consider the basic system to be for pressure, velocity, and temperature. And all additional fields are called composition, but they can be anything else. And the main difference in terms of the equations is that the temperature equation contains a diffusion term, while all of the compositional equations are purely advection equations, which of course contain some numerical diffusion, but there is no physical diffusion happening for these other fields. I hope that answers the question. If not, then feel free to post another question in the chat.